So let's walk through an example of the factorial ANOVA. So in this example, Aaron wants to examine the relationship between gender and clinical track on how elaborate Halloween costumes are. So we're testing for three relationships. We're testing for the gender on the creativity or elaborateness of the costume, probably on a continuous scale. We're looking at the track, so which clinical track students are on their influence, again, on how elaborate their Halloween costumes are. And finally, is there an interaction between gender and track? And if an interaction exists, then we need to test for the simple main effect, similar to post hoc tests. Now, a general note, if this was a more complex factorial ANOVA, I often refer to these kind of analyses as layers of an onion. The first is the overall F test. Is there a significant difference between the IV, or the IV's effect on the DV? For the first IV, gender, is there a significant difference with track on costume? And finally, is there a significant interaction? In this case, it's simply a 2x2 factorial ANOVA. So if we find there is a significant difference on gender, we don't need to do a post hoc test because there's only one potential group that could be different from each other. But if we had three conditions there, then before we ever got to the interactions, we'd also need to do a post hoc test on each main effect. So a main effect, if there's only two levels, we don't need to do post hoc tests. If the main effect is on a categorical IV with 3 or more levels, we also need to do post hoc tests there. If we find a significant interaction, we have to do what's called a simple main effects test to find where the differences are within that interaction. So for example, for males, is the difference between child versus adult clinical tracks on costumes different, or is there a change in how females vary on, again, the elaborateness of their costumes, child versus adult track? So again, we're going to take a look at our data. We're going to actually look at our cells, and in this case, we're basically looking at the marginal means between child clinical and adult clinical, and the marginal means between males and females, but we're also interested in the unique mean differences between all four cross conditions. So again, we have 6 participants in each level. We've rated their costumes, and we find that for clinical males and child clinical, males had a mean of 6, while the females had a mean of 4, so the male costumes were more elaborate. If we look at adult clinical, the males had an average of 6, and the females had a 10. In that case, in the adult clinical track, the females actually had more elaborate costumes. But let's take a quick look at those main effects too. Those child clinical, the overall mean is 5, versus adult clinical, the overall mean is 8, the marginal means. And where we're getting those marginal means are is we're just collapsing the means for adult clinical across males and females. So the males had a mean of 6, the females of 10. We add those together. 16 divided by 2 is 8. Now a quick note, this is always just kind of quick and dirty little ways to visualize this and to think about this. Adding the means and dividing by the groups only works if we have equal numbers. So just recognize that we're kind of taking some shortcuts to just kind of quickly walk through what's going on here. And again, if we look at the top, child clinical, averaging the males and females, 6 and 4 is 10, divided by 2 is 5. Looking at the difference between males and females, again, marginal means, adding the males regardless of whether they were in child clinic or adult clinical, they averaged a mean of 6 on their elaborateness, and the females a 7. So again, if we were talking about just main effects, we would say adult clinical psychologists, grad students, had more elaborate costumes than child clinical, and in general, women, females, had more elaborate costumes than men. But you can see how if we've reported those main effects, if there is a significant interaction, we're ignoring something that's going on here, and that is there is an interaction. It depends on which track you're in and your gender as far as how elaborate your costumes were. So for example, the most elaborate costumes were adult clinical females, but child clinical males actually had more elaborate costumes than child clinical female costumes. So again, just charting this, what we'd actually find is that the males really didn't differ. So it didn't matter if you were an adult or child clinical tracks. If you were a male, your costumes were relatively elaborate. What mattered was the gender interaction, that women in the child clinical track had less elaborate costumes than the adult clinical track. So that's really what's going on. There really isn't a difference between males within tracks. There's a difference within females in tracks. And again, we can kind of see the main effects and potential interaction in this chart. So some other things to keep track with factorial ANOVA. Each factor can have 2 or more groups, so again, we can get as complex as we want with this. The number of levels or groups for one factor does not have to be the same as the number of levels of another factor, so we could have a 2 by 2, we could have a 3 by 3, we could have a 4 by 4, but we could also have a 2 by 4 or a 2 by 6. Factors can be all between subjects, all within subjects, or a mixed design. So we can have one IV be between subjects, for example, exposure to a particular intervention, and the other one be all within subjects. Within each of those exposures, we have multiple subgroups that are appearing in multiple positions. And again, there's no limit on the number of factors. However, the more factors, the more complex the analysis becomes, and the less powerful the ANOVA is at determining and detecting differences. So we're now going to move to the last part that I wanted to talk about in this basic review, which is the ANCOVA, and all we're doing here is we're adding a covariate to any previous ANOVA models. So this could be a one-way, single-factor ANOVA between subjects, within subjects. It could be a 2 by 2 factorial ANOVA. It could be a very complex 2 by 5 by 6 by 4 factorial ANOVA. Anytime that we add a covariate, that's the addition we're making, and we're adding yet another layer to that onion, another thing that we need to look at. The covariate is simply treated as noise. Effectively, we're going to measure a variable that we want to remove from the analysis. The purpose is to give a clearer relationship between the outcome and the predictor of interest. So generally speaking, we're wanting to find something that is varying within the study that impacts the DV, that if we measure and remove will give us a clearer picture, more power to detect what's actually happening. So the within group variance is reduced by accounting for the relationship between the covariate and the outcome variable. In other words, we're using the covariate to remove unexplained variance. In other words, if we can explain it with a variate, a covariate, and then measure that and remove it, we're removing the amount or the size of the effect that's at the bottom of the equation, total variance. So generally speaking, there's a couple of types of covariates. We can do categorical variables that are covariates. We'll usually use this in a blocking design. So we may actually be wanting to differentiate how the effects that we're finding vary from one category or another. A lot of times blocking designs are locations. So these are often used in applied settings where I might be wanting to do an analysis where my data is coming from 3 separate locations. And we can do it continuous, and this is what we're more likely talking about when we're talking about covariates being used to basically increase the power of an ANOVA. And just a quick referral, the difference between a covariate and a suppressor variable, remember the suppressor variable is highly related to an independent variable, but not related to the dependent variable in a multiple regression. And again, even though ANOVA is its own statistical technique, a lot of what's going on in ANOVA is fairly similar to multiple regression. It's just been custom designed to function with multi-layer IVs. In other words, IVs that are categorical and have 2 or more levels. What a covariate should be is highly related to the DV, but not related to the IV, or marginally related to the IV. What we're trying to do is explain variance out of the unexplained variance of the DV to reduce the size of the equation. So you have to ask yourself theoretically, do I have a covariate versus a predictor? Not all extra variance should be removed. An alternate is to examine differences between these extra factors. So is this truly a covariate, something that is simply noise, something that you want to measure and remove, or is it potentially another independent variable? So for example, if we're removing variance of gender, should we be removing that variance between gender, or should we be looking for that difference between gender? So a lot of times also we can use a covariate to adjust for pre-scores or pre-test scores or known bias. So a lot of research that looks at academic performance actually often uses previous academic performance, either GPA, ACT scores, SAT scores, as a covariate. In other words, if everyone was equal in their overall ability to do well in school, are we finding an impact of an intervention that is meant to improve performance in school?